This is a short tutorial demonstrating how to use the web application ShinyKGode to assess the effectiveness of ODE regularization coupled with gradient matching. The ShinyKGode application is based on KGode, an R package that implements gradient matching algorithms for parameter inference in differential equations. Both of these packages can be found on CRAN. We illustrate the concepts of gradient matching and regularization using the Volterra model. The Volterra equations describe the dynamics of ecological systems with predator-prey interactions, for example, foxes and rabbits. In these equations, x1 and x2 are the two states of the model, indicating the numbers of prey and predators. In this system, predators thrive when prey is abundant. Once the predators surpass the food supply, prey population decreases. Finally, as predator numbers dwindle, prey numbers recover. These dynamics repeat periodically such that the prey curve precedes the predator curve. dx1 over dt and dx2 over dt denote the derivatives with respect to time for the two states of the model. Finally, alpha, beta, gamma, and delta are the four parameters of interest which we wish to infer. First, we select the model from the list. In the next step, we can load existing data in CSV format by clicking on the Browse button. Alternatively, we can generate synthetic data by specifying the start and end points of the time interval, 0 and 34, and in the pick field, we indicate how many time points to keep from the numerical solution of the ODE. Here, we use the default value 2, meaning we keep every second point generated by the numerical ODE solver. Furthermore, we can specify the noise of the generated data, either in terms of variance or decibels. In this example, we use noise equals to 6 decibels. Next, we need to specify the ODE parameters. In this example, we use the default values provided, alpha equals to 0.2, beta equals to 0.35, gamma equals to 0.7, and delta equals to 0.4. Lastly, we can specify the initial conditions for the system states, which are to be used by the ODE solver. We then click Generate and the simulated data will appear on the right-hand side, plotted in the form of two time series, one for each state, x1 and x2. This data can be downloaded in CSV format by clicking on the Download Data button. Next, we want to perform parameter estimation using gradient matching. For that, we navigate to the Inference tab. Here we can adjust various settings such as the choice of the kernel. We will use RBF for this example, although MLP, a non-stationary kernel, is also available. We can also adjust the random seed. Furthermore, setting Bootstrap to on will prompt another option to appear that lets the user specify the number of Bootstrap replicates that they would like to use to obtain a measure of uncertainty alongside the point estimates. We advise the user to start with a small number of replicates when using bootstrapping to get an initial idea of how time-consuming this option is for each scenario. Finally, we can modify the initial values of the parameters used in the optimization. We will use the default values here. First, we want to run the standard gradient matching method, and to do that, we need to make sure that ODE regularization is set to off. Time warping is also available, but this option will be covered in a separate tutorial. Clicking the Infer on Generated Data button will run this method, and we can see in the bottom right corner a progress bar that indicates the various stages of gradient matching being performed in the background. Once the algorithm has finished running, the results will appear on the right-hand side of the page. For this example, we can see two time series plots, one for each state, x1 and x2. The noisy observations are shown as red circles, the interpolant is shown as a blue continuous line, the solved ODE with the initial parameters is shown as a gray dashed line, and the solved ODE with the inferred parameters is displayed as a purple dashed line. A table summarizing the results can be found at the bottom of the page. The first column shows the true parameters, the second column shows the inferred values, and the third column provides a robust estimate of the standard error based on the mean absolute deviation. We can download these results as a table by clicking the Download Inferred Parameters button. We can also apply gradient matching with ODE regularization, where the amount of smoothing in the interpolant is decided based on the differential equations themselves. We can run this method by ensuring that ODE regularization is set to On. Note that bootstrapping is still set to On, meaning the estimates will also include uncertainty. However, this comes at the cost of increased computational time. We now click the button Infer on generated data, which will again prompt the progress bar to appear in the bottom right corner. As before, when the algorithm has finished running, this should take minutes for our selected number of bootstrap replicates, the results will appear on the right-hand side of the page in the form of plots and a table of inferred parameters and bootstrap estimates. Looking at the results for state x1, we can see that the solved ODE with the inferred parameters obtained by running gradient matching coupled with regularization, displayed as a purple dashed line, is more similar to the solved ODE using the true parameters, displayed as a gray dashed line, than standard gradient matching. Furthermore, the resulting interpolant from running gradient matching coupled with ODE regularization, displayed as a blue continuous line, is much smoother in the tail and the peak areas compared to the standard gradient matching interpolant. Likewise, comparing the results for the state x2, we notice a similar pattern. The improvement obtained by using ODE regularization can be assessed by comparing the ODE solved using the inferred parameters with the ODE solved using the true parameters. Additionally, gradient matching coupled with ODE regularization improves the fit to the data, especially in the tail and the peak areas. The Diagnostics tab provides information about the optimization step performed during the gradient matching algorithm. More specifically, we can assess how fast convergence is achieved by looking at the plot of the objective function f against a number of iterations, as well as the provided R output with details of the optimization results for each iteration. In this short tutorial, we have demonstrated the improvement that can be obtained when coupling gradient matching with ODE regularization. For more theoretical details about gradient matching or the R implementation that ShinyKGode is based on, please consult the following papers.